Hello and welcome to UCL, one of the world-leading institutions for neuroscience and neuroimaging.
Here we are standing in front of Queen Square Neuroimaging Centre, where numerous scientists and clinicians conduct research, discover innovational imaging techniques, and improve the understanding of how the brain functions.
We are advanced neuroimaging students. My name is Han,
And I'm Harpreet.
and today we'll find out the basic physics behind how MRI works. So, come and join us.
Hello, I'm Barbara. So we want to look at this, but in order to do that, we have to take it out of this, which is not very practical with living patients. So we can use MRI instead to image the brain. Although the brain is the most complex object in the universe, for our purposes, it's just a bag of protons.
Let's find out how the basic physics behind MRI works. So tell me, Han, how does this work?
It's super easy. Most MRI scanners use superconducting electromagnets to align magnetic moments of spins within Lamarck frequency using 3 different gradients to spatially locate spins in K-space, and by using Fourier transform,
Please stop. I have no clue what you're on about. Allow me to explain how the MRI really works.
So the Earth has a magnetic field. You can't sense it in any way unless you're a bird, but for all intents and purposes, it's there. We measure it in Tesla, and it's very small for the Earth, 50 microtesla. So why is this relevant to neuroimaging? Let us zoom in and look at an atom, the atom's nucleus specifically. The nucleus is just sitting happily inside its electron shells. Atomic nuclei also have their own magnetic moments, just like the Earth, and therefore act like tiny little magnets. Importantly, their magnetic moments spin. In the absence of an external magnetic field, the spins face random directions. However, if they're inserted into a stronger magnetic field, let us call it the B0 field, the spins of these protons align in a parallel and anti-parallel fashion with B0. Note the actual protons do not move themselves. Each spin processes at a particular frequency, commonly called the Lamarck frequency, but are often out of phase. Now this is where it gets interesting when we place someone or something into a large bore magnet in an MRI scanner. A clinical scanner has 3 major components: a bore magnet coil to supply the external and strong magnetic field, gradient coils to provide additional and modulating magnetic fields, and transmitting and receiving RF coils to excite the protons and measure the signal from their relaxation. So, you might be wondering, if we have signals coming from all over the object, how do we know where each signal is coming from? To locate the signal, we add additional magnetic field gradients, using the gradient coils to change either the phase or frequency of the proton's precession in the wanted direction. This way, each part of the image will have a radio frequency pulse coming with a frequency and a phase intrinsic to its location of origin. We record the frequency, phase, and intensity of the RF signal for each location and mathematically transform this data set to produce an image. That's all very technical, but luckily, during our course we put together a mini MRI scanner of our own, with the more basic components of a scanner in a much more practical way. After measuring the Earth's magnetic field, which we used as a surrogate for the B0 strong magnetic field, we did an experiment and imaged a bottle of water, which is illustrated here. In our experiment, although the image is far from perfect, if we use a full human MRI, we can illustrate the details of the brain quite nicely.